Okay, good afternoon. Let's start the lecture. Okay, so let's continue on the design for ductile material under static loading. Okay, and I mentioned about two theories that we're going to introduce for ductile material, and the first one is called maximum shear stress theory. Okay, so this is what we have started from previous lecture. Essentially, this is a definition for MSS theory. Failure occurs when the maximum shear stress in the part exceeds the maximum shear stress in a tensile specimen at yield. So in previous lecture, we basically look at this definition, and we can basically look at it. This is essentially a comparison between two quantities. One is this tau max, basically the maximum shear stress in the part, which is what we should try to find out. And the other part is a strength value, and that's the shear stress in tensile specimen at yield at a shear strength value. So number one, this tau max, okay, is always 1/2 times sigma 1 minus sigma 3. So even though you have maybe you have a planar state of stress, and then we'll always put it in the 3D here. So whenever you put it in 3D, and inevitably you will have three principal normal stresses: sigma 1, sigma 2, sigma 3. And sigma 1 is always the biggest one, and sigma 3 is always the smallest value. The tau max is basically the maximum shear stress, which is 1/2 sigma 1 minus sigma 3. Right. And the second quantity, which is the strength value, SSY, the shear strength, and that can be found out by looking at the maximum shear stress in the tensile specimen when it's just about to yield, right? And that we also look at it, and we find it out that this SYT equal to 1/2 times SYT. So SSY equal to 1/2 SYT. And SYT is the yield strength, right? So essentially we're trying to compare the two quantities here. Given the material, you'll be able to find this one by looking up at the tables. And given the state of stress, and you can find this one here. So you literally compare these two, and which one is bigger will tell you whether you have failure or safe conditions. Okay, yeah, that's your MSS theory. So in this part, we're going to look at this in a more detailed fashion at it here. Okay, detail basically, if you recall that in most of the cases in our class, what we're looking at is we look at a plane state of stress. Okay, but we do put this plane state of stress in 3D. In 3D perspective, right? So when you have a 2D state of stress, okay, here is probably your general state of stress represented by sigma y, sigma x, and a tau xy. Okay? And you can always calculate the two principal normal stress based on this state of stress, and that equal to so that equal to this, right? So here you have two principal normal stress calculated based on the plane state of stress, okay, the stress element. And at the same time, when you put it into the 3D, right, for a planar case, you have a third, basically, principal stress, which is always 0, okay? Yeah, always 0. So looking at this MS theory in detail, meaning we're going to look at the three different cases, okay, by the actual values of sigma A, sigma B, so we can we can actually know that which one is sigma 1, which one is sigma 2, which one is sigma 3. So here's the first case. So you could have a sigma A greater than sigma B and a greater than 0. So in this case, I think I summarized previously. Your sigma 1 will be sigma A, your sigma 2 will be sigma B, and sigma 3 will be 0, right? Yeah. So now you can see in this particular case, your maximum shear stress, right? Maximum shear stress. Here's your formula, right, for maximum shear stress. And you look at the current sigma 1, sigma 3. So this is your maximum shear stress. Okay. Yeah. So now MS theory basically says if tau max, right, which is in this case is this, is greater than SYT over 2, and which is your SSY value, right? Then you have a failure. Okay, so we'll have a failure here. Okay. But bottom line is you compare the two quantities, right? You compare the two quantities. So we define ourselves a safety factor, which is basically a ratio. So we define ourselves the ratio safety factor as the strength over the stress. So that'll give us SYT over 2 over sigma A over 2, which is SYT over sigma A. Okay. So this is the safety factor under this case number 1, right? Case number 1 here. So we're gonna do is we're gonna put everything in a graphical illustration at here. Okay, so we're gonna have a graphical representation. You draw a XY coordinate system with X as sigma A and Y as sigma B. Okay, so your sigma A is your x-axis and sigma B is your y-axis here. And then we're going to divide this plane, okay, into, okay, by drawing a 45-degree line at here. So this is your sigma A equal to sigma B line. Okay. Good? Yeah. Now, if we look at the nature of sigma A, sigma B, if you look at the nature of sigma A, sigma B, what is it? Sigma A is always what? Greater than sigma B. Okay? So sigma A is always greater than sigma B. Then on this plane at here, so we're actually not looking at everywhere. So we're literally just looking at which half? The top or the bottom? The bottom here, right? So we're going to just basically focus on the bottom here, okay? Yeah. So the first case, right? You look at the first case here. It's a sigma A greater than sigma B greater than 0. So so both sigma A and sigma B are greater than 0. So which means you are literally just where? Just on the first quadrant here, right? Just first quadrant here, because that's where both values are greater than 0. Okay? Yeah. And the safety, what the safety telling us is, basically when this sigma A greater over 2 greater than this over 2, or sigma A greater than SYT, right? If this is greater than SYT, then you have a unsafe region, right? Unsafe, basically. So we can label this SYT at here. Then for any values beyond that SYT in this quadrant, right, in the first quadrant. So if sigma is greater than that, then you have a failure for this ductile material. Or if this is less than that, right, if it's over here, then you have a safe region at here. Okay? Yeah. So that's what basically the first case corresponding to this area. This area will be safe, right? Outside over here, and I will be unsafe. Is that clear? Yeah. Okay, so that's your first case. So let's look at the second case at here, right? Second case. Second case, sigma A greater than 0, greater than sigma B. Okay. For the second case, it corresponds to sigma 1 equal to sigma A. And the 0 is sigma 2. And then sigma 3 is the sigma B. That's the second case. The three principal normal stress, right, will correspond to the three existing stresses like that. Okay. And so now your tau max, okay, is basically same thing, sigma 3, 1 minus sigma 3 over 2. And now it's sigma A minus sigma B over 2. Right? That's your tau max. Okay. And you can still write the same statement as the previous case 1. You can see that if your sigma A minus sigma B over 2, which is your tau max, is greater than 1/2 SYT, okay, or get rid of the 2, it's equivalent to C okay, or the sigma A minus sigma B greater than SYT, then we have a failure, right? Okay, so that's the point in here. Okay. Now, how do I illustrate the second case in this plane then, right? In this plane. So let's look at before we look at this one here, we can write down the same thing, the safety factor. So now you can see the safety factor is just a comparison between the tau max and the strains. So we can still write the safety factor as a tau max strain, so that basically gives us SYT over sigma A minus sigma B, right? Here's your safety factor. Comparing SYT with tau max, in this case, then you get SYT over sigma A minus sigma B. Okay, and n equal to 1, right? So n equal to 1 is the critical, right? This is the critical here. Okay. When n equal to 1, you have a critical boundary, and the critical boundary at here corresponding to this SYT equal to sigma A minus sigma B. This is your boundary. Okay, here's your boundary at here, right? This is your boundary. So what is this boundary on the plane at here, right? On this plane here. So this is essentially xy plane. Then when you look at this one here, this is like x minus y, right? So your x-axis, y-axis equal to a constant. So that's a straight line, and this straight line here is actually pretty simple. It's basically a line connecting from here to here, and this is your negative SYT. Okay. So this line at here is your sigma A minus sigma B equal to SYT. So that's this line here. Okay. So for this particular line, and then you can think about it basically. Let me write down here. This is your sigma A minus sigma B equal to SYT. Okay. The safety statement basically saying is, if this quantity is greater than SYT, it's unsafe. If it's less than SYT, then it's safe, right? Yeah. So what that means is, whenever you're within this region here, then you're safe. If it's beyond that, then it's unsafe. Okay? Yeah. So that's basically what this boundary here represents. Good? Yeah. Now, within this region, right? Within this region, there is actually a special situation. So if I draw a line like this, let's see, if I draw a line from here to here, and this line is sigma A equal to negative sigma B. Okay? So if you draw a line like this, sigma A equal to negative sigma B. So what does this sigma A equal to negative sigma B actually represent, right? So now if you think about it, okay, this is basically called a pure shear line. Not pure shear, it's pure torque. Yeah, that's right. Yeah, pure shear line here, or pure shear load line. Okay. Yeah. So if you think about a scenario like what we I think we covered through an example. So let's say if you have a bar at here, and then you subject the bar with a torque, right, on both sides. Okay, you subject the bar on the top both sides here. Okay. Yeah. And you can essentially take a stress element cut anywhere. You take a stress element at that location. If you take a stress element somewhere, basically on the cross section, right, on the cross section here, and then you draw, suppose let's say you draw most circles, okay, based on that stress element. So if you take a stress element, okay, so all you see is essentially, you see that you have only shear stress exists on the stress element, okay? And then when you draw the Mohs circle based on that stress element, so using that steps we learned, drawing a Mohs circle, you get a circle centered around the origin, right? You get a circle centered around the origin. And this particular circle gives you a sigma A and sigma B. And the connection between the sigma A, sigma B at here is what? Is sigma equal to negative sigma B. Okay? Yeah. So that's why for this particular line at here, we call it pure shear loading line. So this line here, you can consider it's some sort of a pure shear applied to a certain bar here, right? Which will yield a sigma A equal to the negative sigma B. Okay? So that's what this pure shear line here means. So why is this pure shear line sort of special line? Well, how do you get the tensile strength? Through what type of experiment? What type of experiment will give you the tensile strength or tensile yield strength? What type of experiment can give you that tensile strength? Tensile test, right? And what type of experiment can they give you the shear strength? Torsional test, right? Torsional test, which is what type of test? This is a torsional test, right? Yeah. So if you look at this line here, this is essentially like you can literally think of this as doing a tensile test at here, and that test will intersect with this boundary at a certain point, right? At a certain point. So that point basically will correspond to that shear strength. Okay, the points SSY here. Okay, yeah. So what you can do is you can look at, this is the line equation. Here's the line equation at here. So I can have a line equation here and another line equation over here, right? So there are two line equations. And solving the two line equations to get to the intersection point, right? Intersection point. So this intersection point will give us a value sigma A equal to SYT over 2. Okay? Sigma A equal to SYT over 2. So basically at here, if you draw it upwards, okay? So this is your SYT over 2 at here. SYT over 2. Yes.
This is still only for case 2, right?
This is still case 2. Yeah. Is that good? So now looking at the Mohs circle here, when sigma A equal to SYT over 2, what is the shear? What is the shear stress at here? This is a radius, the same radius at here, right? So the shear stress is the same value as SYT over 2. Okay, and that basically actually conforms with this MS theory at here. The MS theory that we derive here, what's the value of SSY? SSY we derive is 1/2 SYT, isn't it, right? Yeah. So over here, the connecting point give us basically the SSY value, right? So your SSY value is basically 1/2 SYT here, okay, from this one. Okay, it conforms this SSY value. Okay, so that's your second case. So second case give us this line at here. This first case give us, and let's look at the third case. The third case is when 0 is greater than sigma A and greater than sigma B. So that basically means your sigma 1 is 0, sigma 2 is sigma A, and sigma 3 is sigma B. That's the third case. So for this case, tau max is 1/2 sigma 1 minus sigma 3, sigma 1 minus sigma 3, so negative sigma B over 2. Again, if you compare the tau max with SSY, if this is greater than SSY, then failure. Okay, so you get a failure here. Safety factor will be a comparison between the strength over the stress, or it's negative SYT over sigma B. Very similar approach as the case 1 and 2. Okay. So when n equal to 1, which is the boundary, and you get your sigma B, you get your sigma B equal to negative SYT. Right. So that's the boundary here. That's the boundary. So coming back to the graph, right? To the graph to finish this graph right here. Basically, the boundary in this case is this. Okay. So this is your, and then when it's above that line, you're safe. If it's below that, then it's unsafe, right? Yeah. So overall, the three case will form the bottom here. Will form this. Okay, will form this. Yeah. For more of a emphatic point of view, we can mirror the bottom here to the top. Okay, so to make the so-called basically a hexagon at it here. Okay, so we got a hexagon. So overall, the MSS, it's safe within the hexagon and it's unsafe outside. But in reality, actually, we're not going to be able to reach this because our case sigma A is always greater than sigma B. Okay. Yeah. So this is basically the graphical representation of this MSS theory right here. Okay. Yeah. In short, all you need to remember is basically these two. That's it. That's the basically the formula for MSS. Right. Okay. So let's look at now. Let's look at the other theory. Okay, for ductile material, which is the distortion energy theory. Okay, DE theory. For distortion energy theory, let's take a look at what does it say basically in terms of the failure, right? Okay, so before we talk about distortion theory and distortion energy theory, right? There's a phenomenon that we have to point it out first. Okay. Yeah. If you have a ductile material, okay, or ductile a part made of a ductile material, okay, and if you stress these parts, okay, hydrostatically basically means you're like putting it under the water, and the pressure is evenly applied to every side of this part. Okay, so that's basically what it means by hydrostatic. Or you pull this part. Okay, you pull this part evenly across all sides, okay, across all directions. So that's what we call hydrostatically, okay, to stress these parts here. Now, if you do this, and there's a phenomenon, you'll notice that in this case, okay, if stressed hydrostatically, okay, and we notice that the yield strength, okay, is actually greatly larger than the value given by a simple tensile test. So that's a phenomenon that you can observe, okay, if you stress these parts hydrostatically. The yield strengths are actually well beyond the yield strengths when you subject the part to a simple yield test, tensile test. Okay, yeah. So then people looking into this phenomena, basically the conclusion in it here is the yielding is not just a simple tensile or compressive phenomena. So it's not just a tensile or compressive. It's more have something to do with this, the so-called angular distortion of this stress elements. So this is basically leading to the concept looking at the angular distortion of the stressed element. Okay, stress element. And the angular distortion of this stressed element, okay, that essentially asking us is, okay, so let's look at this one here, which is the concept called distortion strain energy. Okay. How much distortion strain energy is there? If it's too much, then you have a failure, essentially. Okay? Yeah. So that's actually where the name of the theory comes from, distortion energy theory, right? Distortion energy theory. So we'll look at distortion strain energy, and then we'll use these results we'll derive for the DE theory here. Okay? Okay, so let's look at the definition first. Okay, just as the MS here. So here's this DE theory. And the DE theory states, okay, that, so I'll write it down and then let's read it, okay, just like the other one here. Let's read it carefully, and then once I write it down here. Failure occurs when the distortion strain energy in the material exceeds the distortion strain energy in a tensile test specimen. Of course, they should be the same material, okay? At yield. Okay, so that's the DE theory. Okay? It's very simple. Once you're finished, then we can analyze this sentence that are here, okay, and see what it really means here. Okay, so let's read it again. Failure occurs when the distortion strain energy in the material. So that's your first quantity. Okay, this is one quantity here. exceeds another quantity, exceeds, what's the second quantity? Exceeds the distortion strain energy in the tensile test specimen at yield. So this will be the second quantity, right? If the first quantity is bigger than the second quantity, then it's failure. That's basically what the DE theory described it here, right? Yeah. So now let's look at the detail now. So what is number one, right? Number one is saying the distortion strain energy in the material. So basically, we need to find out what is the distortion strain energy. And second quantity says that there's still an idea distortion strain energy, but this is a distortion strain energy at a specific condition. It's in the tensile test specimen at yield. So you test the tensile specimen, and when it's yielding, at that moment, what is the distortion strain energy? Right? So you're comparing the two distortion strain energies. Okay? Then you get the DE theory here. Okay? Yeah. So this is what we'll do, and we'll look at basically the quantity here. Let's look at the quantity here called distortion strain energy. Okay? Distortion strain energy. So we'll call it using a UD here representing this distortion strain energy. So first, let's look at just the distortion strain energy. It's in general, right? In any material or in any parts, okay, under certain stress conditions, okay, loading conditions. So I'm going to write it down first, and then I'll explain it. My lecture notes has a very detailed proof for what I'm writing down in it here. Okay, so the distortion strain energy expression is this guy. Okay, yeah. So this is our expression for distortion strain energy. It's 1 plus V over E, which is Young's modulator, and the V at here is called Poisson's ratio. And E is the Young's modulator for the stiffness, and sigma 1 to sigma 3, they are the principal normal stress. Okay. So this is your distortion strain energy. So let's call this as equation number 1. This is basically the first quantity, right? The first quantity. That quantity 1 over here. Okay. So of course we're going to try to derive this distortion strain energy in a tensile test specimen, right? Yeah. Now, how is this derived? I won't give you the detailed proof of it here, but the idea to derive this one here is this. So let's say you have an element, okay, stress element taken from the parts under certain loading condition, and it's very well could be summarized as stress element under a 3 principal stress, sigma 1 to sigma 3. Okay. So here is a typical general state of stress, right? Then this one here, we can derive a so-called total strain energy first. Okay, so for any stress element, you can always derive a total strain energy first. And total strain energy is equal to this. U equal to 1/2 sigma 1 epsilon 1 1/2 sigma 2 epsilon 2 1/2 sigma 3 and epsilon 3. And this epsilon 1, 2, 3, they are basically the strains under sigma 1, sigma 2, sigma 3. So you have a stress on this side, and there's probably strain, corresponding strain sigma 1, similar to sigma 2, sigma 3. So you got your total strain energy like this. Okay? Yeah, total strain energy. Now, for this one single stress element, which has a total strain energy expressed over here. And you can always separate the string energy of this stress elements into two components. Two components. Now the first component is considered basically consider it's a hydrostatic. This is a hydrostatic component. Which means every side are under the same stress sigma AV, and then you can call the corresponding strain energy as a UAV at here, corresponding to that state. And this one over here, the rest of the basically this is your sigma 2 minus this, sigma 1 minus that, and sigma 3 minus that, right? Yeah, the rest of the stress. And this one is exactly what we're looking for. This is basically the so-called distortional parts. That's the parts under a distortional stresses. And the corresponding calculation, you can get this so-called UD, which is basically you get a distortion strain energy. So that's the roughly the steps. If you look at the lecture notes, basically what you'll follow through here. Basically get the total, calculate the hydrostatic component, then this UD, right? You can literally say UD, which is basically equal to this total minus this UAV. And finding this, and you'll find the UD, and which is the expression that I gave out here. Okay? Yeah. So that's your total strain energy here, right? Total strain energy. And this is your quantity number 1. And as I said, we do need to compare 1 with number 2, right? So number 2 is a special distortion strain energy. It's special basically means what's the strain energy in a tensile test specimen at yield. So let's look at the quantity number 2. So essentially we need to ask the question is, what is the UD for a tensile test specimen at yield? So what does this quantity equal to? And this is your second quantity, right? This is second quantity. If we can find this one here, then we'll just compare our first one with the second one. Okay. So let's consider this tensile test at specimen, the tensile test. So when you have a tensile test, this is what happened. You have a force applied to both sides of the specimen. And if I cut a cross section and looking at an element on the cross section, and basically we have nothing else but a tensile stress. That's your basically the state of stress. And when this state of stress at yield, your sigma x basically equal to SYT, right? At yield will give you this condition, sigma x equal to SYT. Very good, right? And if you look at this state of stress, and you can summarize, okay, for this state of stress, my sigma 1 will be SYT, sigma 2 is 0, and sigma 3 is 0. So basically, if you substitute right into the principal normal stress formula, you get your sigma A equal to SYT, sigma B equal to 0, and then sigma 3 equal to 0. So this is basically what we need to do to substitute into the general formula for the distortion strain energy, which is given in that equation number 1, right? So sub into equation 1, right? Sub into equation 1. So look at equation 1. Here's your equation 1, and here, right? Equation 1. Okay. So sub into equation 1, what do we get? We get UD equal to 1 plus Poisson's ratio over, and then 6E, and 2 times SYT squared. Okay, 2 times SYT squared. That's the distortion energy for a tensile test specimen at yield. A little bit of simplification give us 1 plus V over 3E SYT squared. Okay, so we are done with the value for quantity 2. So now you have quantity 1, you have a quantity 2, and time to do comparison, right? By applying the distortion theory energy. So distortion theory, so the DE theory, okay, says failure occurs when number 1 quantity is greater than number 2 quantity. So I'm going to just basically looking at this number 1 and number 2, there are many things can be cancelled, right? So number 1, you have a 1 plus Poisson's ratio over E. Number 2, you also have 1 plus Poisson's ratio over E. So if you compare these two, we end up with this expression. Okay. So if this side is greater than the other side, then you gotta feed it. Alright? Yeah. That's basically what DE theory mathematical representation. Calculate this side, compare to that, and you got a feeder. Okay? Yeah. But we typically what we actually calculate are not these two. So we do this. Divide the 2 on both sides, so get rid of 2 here, and then take a square root on both sides. So this side here will be just SYT now, and then this side here will be okay, that will be this. So here is your basically almost the final version for DE mathematical representation. Because this is exactly in a format of what? Comparing something with a strength, right? With a strength set here. Okay. So the left side, okay, the whole left side of it here, we use sigma, we call it sigma prime. The whole left side, we'll call it sigma prime. And this is called von Mises stress. Okay. Von Mises stress. This is very important quantity, von Mises stress. And if you run a lot of typical, if you run a typical stress analysis software, and one of the important quantity you probably want to calculate is von Mises stress. And how is that calculated? And that's basically this formula here. Okay, that's von Mises stress. And we use sigma prime to call this. So bottom line now, you can see, okay, so what's the safety factor calculation, right? You can calculate safety factor basically by comparing the strength, which is the yield strength here, with the von Mises stress sigma prime. If it is greater than 1, you are safe. If it is less than 1, then it's failure. Okay? Yeah. So I should. This is basically what I write it here is failure. Okay? So this is a failure here. Okay? This failure. Those are failure cases, okay, when it's greater. Good. So that's it. That is the DE theory. That's the DE theory here. Okay. Now let's look at just maybe a couple of comments that are here. Okay. And before we look at an example, remember the one that is written at here is a general formula, okay? For 3D, you have a 3 principal normal stress. But in reality, when we're dealing with the reality, is most of the cases, as I said, it's always a planar state of stress. So maybe we should just look at what would the D look like if we look at just the plane state of stress. Okay, if we just look at the plane state of stress, and how does this D theory look like here? Okay, so planar state of stress basically means you have nothing but these 3 state of stress: sigma x, sigma y, and tau xy. And then this will yield 3 principal normal stress. One of them is 0, and the other 2 are the typical sigma A, sigma B principal normal stress that you can calculate from the formula, right? So I don't know which one is sigma 1 or which one is sigma 2 or which one is sigma 3, but if you look at the von Mises stress set here, right? And the nice thing here is it's always square, square, square here, right? So you can literally let's say if you literally let any one of them, any combinations, let's say this is 0, maybe 0, sigma A, sigma B, or sigma A, sigma B, 0. So any combinations, right? You can literally put in any combination. Any combination will yield actually the same result. So all of the results will give you a sigma prime equal to this. Okay. That'll give you the same value for the sigma prime, right? Same value for sigma prime, which is always this one right here. Okay, that's always this one. So that essentially is saying, okay, so if you wanted to check the safety using D theory, then all you need to do is to compare this quantity with SYT, right? This quantity with SYT, and you'll get the answer. Okay? Get the answer. Now, you do have the formula for calculating sigma A, sigma B, right? You know, sigma A, sigma B calculations, which is what is it? We write it down there. This is your calculation sigma A, sigma B, right? Yeah. So if you substitute this expression into here, okay? If you substitute into here, you get another alternative expression. So that'll give you another one here for the sigma prime. So that's another expression for sigma prime. So these two, okay, they're all good. They're all good in terms of the calculation for sigma prime. Or you basically now you compare SYT, right, using this expression.
This is only for plane state, right?
That's right. Yeah. Because all involved here is just sigma x, sigma y, tau xy, right? Yeah. If you have a 3D state of stress, then you will have sigma z and tau xz, tau yz, right? It will be different. Okay. Good. Now, let's take a look at this expression again, right? So let's maybe focus on this one here again. So we're saying you compare this square root with SYT. Okay. Now, basically, I can also see that there is a boundary. There's a boundary condition, which is this one. So if I let this equal to SYT and then square each side, I get a boundary condition, right? So here you get a boundary condition here. Okay, yeah, you get a boundary condition, and outside the boundary it's unsafe. Inside the boundary it's safe. That's basically what this means. Okay. But what does this boundary look like then, right? So now if you look at this expression, okay, this is basically an expression representing this boundary. Now if I draw if I think of sigma A as x and think of sigma B as y, and SYT is some constant, so I can literally basically plot this out, right? Plot this out. And when you plot it out, and you'll see that this is an ellipse. Basically, you end up with an ellipse at here. Okay, it's a tilted, more or less like a tilted egg, like this. So it's an ellipse rotated by a certain counterclockwise by a certain angle. Okay, so you got an ellipse at here. So that's basically this boundary. Yeah. So mathematically, basically, this represents a ellipse equation, right? Yeah. Well, the typical ellipse equation is like x squared over 4 plus y squared over 9 or something like that, right? Yeah, that's typical. Yeah. But this is also an ellipse equation. Okay. Yeah. But this equation is horizontally, okay, lying there. Okay. Now let's look at this ellipse set here. Okay. Let's look at the ellipse. And now I'm going to look at a very special situation, and which actually we talked about when we talk about MS theory. So I'm going to look at this sigma A equal to negative sigma B situation, right? Yeah. Now if you recall that when sigma A is equal to the negative sigma B, and for this line at here, this is, remember what we call that? It's a pure shear, right? So basically, this is like everywhere along this line here, you're like doing a torsional test essentially. Okay, yeah. So you can imagine for this particular line and intersection with this boundary for the DE theory, so this one here must give us a very special value here, right? Yeah. So I'm going to do the same thing as we did previously. I'll put down the two equations. One equation is this pure shear line, and the other equation is the boundary condition. Okay. Yeah. So I can solve for intersection between this straight line and this ellipse. So solving for this one here, you get your sigma A equal to 1 over root 3 SYT. So you get a value for the sigma A which is equal to this. So that's basically your maximum sigma A you could have when you apply this torsional test, right? Yeah. And that torsional test give us the so-called shear strengths. Okay, shear strengths. And this shear strength that here, this essentially, if you remember that most circle, the tau max corresponding to the value of sigma A. And this one here, okay, which if you calculate what root 1 over root 3 is 0.577. And this one here is basically your shear strength value, SSY. Okay, SSY. So according to DE theory, basically according to the DE theory, it predicts that the shear strength to be 0.577 SYT. Okay. So back to the MS theory. In MSS theory, what does MS predict, or what is the shear strength under the MSS theory? In that MSS theory, SSY equal to, what is that equal to again? 0.5, right? So if you compare to this one here, apparently the DE is slightly bigger, right? Slightly bigger. So we can actually superimpose the two sketches together, the DE and MS theory together. So we'll see that once you put these two together, you get a relationship like this. The black one is inscribed inside this DE theory. With the black one represent MSS, and the green one is this DE theory. Okay. Yeah. So apparently you see that this explains very well graphically. The DE theory predicts a less shear strength compared to the shear strength predicted by the DE theory, right? Yeah. So here's a question. You have a MSS theory and you have a DE theory. So you could calculate a safety factor based on MS or based on the DE, right? Which one is more conservative? Yes. Exactly. Right. So MS is black inside the DE. If I pick a point over here, sure, both theory consider this is safe, right? But if I pick a point over here, guess what? The MS actually consider this is a failure, but then the DE actually still consider this is what? A safe. Okay. So MSS here is more conservative. And sometimes this is a multiple choice I give to you in the midterm. So which one is more conservative, essentially? Okay. When we learn brittle material, we also have different theories. We'll have the same question, and which one is more conservative? Okay. Yeah. That doesn't mean that more conservative is better. Okay. Yeah. If you look at there is a plot of experimental data. Basically, plot the results of the data, and also plot the MSS and the DE. So you'll see that a lot of this data here are basically centered around the DE theory. Okay. Yeah. So DE theory, in principle, is more accurate than the MSS theory. Is that good? Yeah. But of course, MS theory here is apparently more conservative, right? Okay. Yes.
The DE is more accurate?
More accurate. Yeah. So basically, the data points were mostly along the DE boundary lines. Yeah. Okay. So let's take a look at the quick example right here. Right? Quick example. Let's say we have a material given it's a steel, and its yield strength is 100 psi. Okay, and we somehow already calculated the already calculated sigma 1, 2, 3, and let's calculate the safety factors, okay, using both MSS and the DE theory. But before we proceed, and I just want to reinforce the idea here. Now, if you're given sigma 1, sigma 2, sigma 3, can you immediately write down which one is sigma A, which one is sigma B, and which one is 0? You got a 0 here, right? Yeah. So in this case here, which one is sigma A? Good, right? Yeah. You do need this. You do need this if you use a formula, right? That corresponding formula for calculate sigma prime. So let's calculate sigma prime first. So I choose this formula. Turned out to be 88.9 KSI. So now we're ready to calculate the safety factor now. If I use MSS theory, the safety factor calculation is always just SYT over sigma 1 minus sigma 3, and that's 100 divided by 70 minus, so become positive, so that's another 100, so which is 1, right? If you calculate using DE, it's comparison between SYT and sigma prime, so it's 100 over 88.9, so that gives us 1.13 approximately. Okay. And this does absolutely make sense because we said MS is more conservative, so the safety factor calculus should be slightly less than the DE theory, right? Yeah, which is the case. Okay. Yeah. Okay. Very good. We'll look at more sophisticated example rather than this one here, just shortly. Okay. Before we do that, and then I also wanted to introduce another method of calculating safety factor. Okay, if you don't have your calculator, happen to have a calculator, then how do we calculate our safety factor here? Okay, so I call this as more or less calculating safety factor using graphical approach. Just a ruler will be enough. Okay. So here's how you would proceed when you have this kind of situation. So you're given, for example, a certain material, for example, 220 megapop, and then you also have the loading condition or stress of elements, and we want to know what n equal to, okay, using MSS theory. Okay. Yeah. So here, this is basically exactly type of a question like what we just did, right? And you can use the formula to calculate the MSS and do a division. That's fine. Okay, but and you forgot your calculator, and you also forgot how to do a division. So then what do we do, right? And that's almost impossible, but let's assume that's the case. Okay. So here's what you would do graphically. Draw the sigma A, sigma B coordinate system. Okay, and then you can see that your SYT is a 220 megapop, right? 220 megapop. So use a ruler, use a paper, and then you see, okay, let's say this is 1 inch. Okay, use a ruler, this is 1 inch right here, and then you make a note. Okay, so this is a 220 megapop. Okay, this is 220 megapop here. That's your indication of scale. So this much represent 220 megapop. And then here is your sigma A, sigma B. So we label or we find the coordinates using sigma A, sigma B as a pair. So sigma A is 100, sigma B is 80. Sigma A is 100, so 100 is approximately a little bit less than half of this 220 megapop, right? So let's see, this is a half here, and then slightly less than this half of the 220. And sigma B is slightly less than 100. Okay, so and this is your 100, so slightly less than that. So I don't know. Let's say this is a location here, right? This is a location. Okay, so this location right here is your state of stress. Let's call this as A location. So this is your A location, which is the current state of stress. Okay, right? So you can do this, all of this, by using a ruler, right? Yeah. So now let's basically apply the MS theory. So MS theory, basically when we apply MS theory, what we do is we draw that hexagon, right? You can draw the hexagon using the SYT, and then here is negative SYT, so this is easy. Using ruler, you can definitely draw it out. Is that good? Yeah. And now, you have your sigma A at here now. So the last step, what you do is, you draw a line, okay, connecting OA, okay? You draw a line, okay, out of the OA at here. And that line will intersect with the boundary at B location. Okay? Yeah. And once you finish this at here, you can use your ruler. Okay? Use your ruler here. Okay, how much distance from O to A? And use your ruler to calculate how much distance from O to B. Okay? So calculate your distance here using the ruler OA and OB, and then do a division between OA, OB and OA. So this will be your safety factor. So again, you have to do a division here, right? So that's graphically how you can get this safety factor, right? How you can get the safety factors. Okay. This is actually quite an interesting thing if you look into this a little bit deeper at here, right? Yeah. So let me ask you a question here. Basically, let's see. So for example, right? If this is A here, if I'm gonna pick another location. Let's see. I'll pick a location C at here. So C is directly under the A location. Okay? Right? C is directly under A location. So of course you could do the same thing, right? For the C location, you have OD over OC, right? Yeah. So here's this quick question here. The safety factor, right, corresponding to the state of stress at A, and the safety factor corresponding to the state of stress at C, are they the same or are they different? Using geometry. Let's call this N1 as N2, right? So the N1 and N2, are these different or are they the same? Anybody? It's the same, right? Geometry, high school geometry. OD over OC, OB over OA, they're all equal to what? This one divided by this one here. Right? Yeah. So they are the same. Okay. So you see, you have a different state of stress. You have the same safety factor. Okay. Yeah. That graphical approach, okay, sometimes explain differently. So there's also this scenario here, right? There's also this scenario. Let's say, for example, right? If I have a location in this domain, okay, in this quadrant, so I can do the same thing. I will just draw here to here. Let's say this is E, this is F. So I get let's say N3 equal to OF over OE, right? Over OE. Okay. Yeah. Now, if I pick a different location, if I'm going to pick a location over here, and that location happen to be basically on the parallel line, so this line here and this line here are parallel, okay? Yeah. And let's call this is W and V here, okay? Yeah. So using the same idea of a geometry here, you see that the N4, right, equal to OV over OW, okay, because these two lines are parallel. So this N3 is actually the same as the N4. Okay? Yeah. Is that good? Yeah. So that's just the alternative if you just happen to not have a ruler, then you can always basically calculate using this graphic approach. Okay, so let's take a look at another example. So the example is more an example to put it into an actual loading condition, actual case like this. Okay, so I'll draw something to illustrate this particular case. So let's say we have a bar, okay, fixed to the wall. Okay, so this bar here is fixed to the wall, and then this is actually, there's a crank at it here basically. So on this side here there's a crank arm. Right, so this arm is over here, and now you have a force applied at the end of the arm. Okay, so what we wanted to do is suppose that all the material of the rod are made of the steel or aluminum, is a ductile material, for example. Okay, so what we wanted to do is we want to use the MSF theory and also probably DE theory to find out, first of all, to find out where the critical locations is, and what will be the safety factor at the critical location, or whether it will fail or not due to this loading condition. So that's basically what we want to do for this question right here. Right? Yeah. And a few parameters for this question right here. Let's say this rod here has a length L, and then this side of arm has a length A. The rod has a diameter at here, which is a D. Okay, so here is L equal to 6 inch, and A equal to 8 inch, and D is 1.5 inch. The F is 1,000 pound. Okay. And your material has 47,000 psi for the yielding strain. That's it. Right? That's the loading condition. That's your strains, and we want to find out the safety factors for the critical location. Okay. Yeah. So what do we mean? First of all, when you have a system here, what do we mean by critical location? So the critical location must be where? Must be location that has the possibly, right, maximum stress. Okay? Yeah, I don't care what kind of stress. Must be a location possible that has the maximum stress here. Okay? Yeah. So maybe looking at this one here, what do you think? Where would be the critical location? Where would be a possible critical location for this system? Is it going to be somewhere here? Or where else could it be? Yes? The top of both, you mean the wall? Right? Yeah. So that's right. So this is a critical location at the wall location, right? This is a wall here. Okay? Yeah. Why? Because this is all about basically static now. When you have a force applied at here, when you walk along this system, basically what type of a distribution of a force or moment along the system here. That makes sense, right? Yeah. So you have force applied here, and then there will be a force felt by the system everywhere, right? And when you walk along here, so there will be basically, for example, this corresponding to this point will cause a moment, and this corresponding to this point will cause also a moment, right? Yeah. But really depends on basically the distance also, isn't it, right? But if you think about this force with respect to the wall, right? This force with respect to the wall here, what type of moment does this force will cause respect to this wall. Now, how many moments caused by this force with respect to the location of the wall here?
2.
Yes, right? 2. Okay? And you can think about what the direction of the moments. Moment is always the r cross f. Okay? So the displacement cross f. So from here to here, you can have a displacement. From here to here, you can have another displacement. Right? Position vector. Okay? So r cross f, f causes moment in this direction, and r2 causes moment in this direction here. Right? Yeah. That make sense? Yeah. So which one will try to cause this rod to rotate about its center axis? Which one will try to cause the rod to rotate about the center axis? R2, right? So in this case, this is also basically in our class here. For this R2 cross the F here, it's a moment, okay? We call it T, okay? So we call it the torque. And for this R1 cross the F, it's going to be a moment. Okay, so this is what we call this one is a moment. Okay, but both are moments actually. So basically, this is a question: when do we call it torque? When do we call the moment a torque, right? Instead of call it a moment. Is that clear? Yung? Yes.
Force is pointing downwards, right? Not
yeah, pointing downwards.
upwards.
Yes.
And R1 is pointing parallel to the rod.
Yes.
And R2 is
Parallel to this arm. Yeah. Right. So this is basically in this class, basically the simple question. Maybe you not. What's the difference between torque and moment? I'm not sure if you think about it yet, right? The simple answer is you call it torque when it try to cause the bar or the rod to rotate about the center axis. Okay, yeah. But torque is basically a special case of moment, essentially. Okay. Yeah. Okay. So symbol-wise, that's it, right? So now we're going to look at the critical location, the wall location at here, and then the wall has many locations, right? There's infinite number of locations here, but we're not going to look at all the locations. So we're going to look at is one location on the top, okay, right there, and the other location we'll look at is this location here, okay, yeah. So if you think about the scenario we described in the previous lecture, basically when you cut a cross section, when you draw an axis like this is more or less like a neutral axis, right? And this is your A at here, okay. So what's the difference between A location and a B location? For A location, there's a maximum, what type of value? When we do the stress analysis, the A always have a maximum bending normal stress, and B always have a maximum what? Shear stress, right? That's why we'll pick just A and B location to do the analysis at here. All right? Yeah. So I'll finish analysis in the beginning of the next lecture, okay? And then we'll get on to the brittle material next lecture. Any questions? Yes. Yeah. Come here. Yeah. Come here.